Understanding the dynamics of ultrafast laser-induced solid-to-plasma transitions is a complex multiphysics problem involving atomic, solid-state, plasma, and laser physics. The preplasma formed during the laser pulse's rising edge is particularly challenging to access experimentally and theoretically. This research focuses on the initial stage of the interaction, providing a detailed visualization of preplasma formation and evolution. Using nanometer-thin diamond-like carbon foils, the authors demonstrate the transition from solid to plasma during the laser rising edge with intensities below 10 to the power of 16 W per square centimeter. Single-shot near-infrared probe transmission measurements reveal sub-picosecond dynamics of an expanding plasma with densities above 10 to the power of 23 cm3. The authors highlight the importance of precise knowledge and control of the preplasma, as it crucially affects the efficiency of laser-driven ion acceleration. They discuss various ion acceleration mechanisms, including radiation pressure acceleration, RPA, and target normal sheath acceleration, TNSA, which depend on the preplasma state. The research emphasizes the need for accurate modeling to identify tunable key parameters, particularly in the context of relativistic induced transparency, RIT, schemes. The authors suggest that fine-tuning the target state before the pulse peak's arrival requires a deep understanding of the interplay between ionization, collisions, and expansion. The study's findings have implications for applications such as laser-driven ion acceleration, material testing, and cancer therapy. Ultrafast transitions from solids to overdense and expanding plasmas are triggered by the steep rising edge of femtosecond laser pulses with peak intensities exceeding 10 to the power of 16 WCm². To investigate this phenomenon, a pump probe approach is employed, combining single-shot near-infrared probe light transmission measurements with a two-step interaction model. The laser contrast profile, shown in Figure 1a, is accurately described by two fitting curves, essential for subsequent data analysis and modeling. The steep rising edge, occurring within the time window 3.7 ps is less than or equal to T_pump is less than or equal to 0.2 ps, is particularly relevant, with an intensity profile I equals I_peak CR, where CR is the contrast ratio given by express T_pump, 277 fs, and I_peak is the maximum intensity at the pulse's peak. To ensure plasma formation during this steep rising edge only, the peak intensity I_peak is reduced to approximately 10 to the power of 15 WCm², such that significant ionization commences after T_pump approximately 4 ps. This steep rising edge spans about 5 orders of magnitude in intensity, a critical aspect for plasma formation and subsequent acceleration processes. In the high-intensity region of the focal spot, plasma dynamics are central to understanding the interaction process. A temporally chirped broadband probe pulse is used to diagnose the interaction region in the transverse Y direction and in time, achieving sub-picosecond time resolution within a single shot. The plasma profile in the transverse Y direction mirrors the focal spot shape and size, indicating that the laser's first low-intensity airy ring induces the wanes. Particle densities are expressed as a function of the critical plasma density for the probe wavelength. Absolute transmission measurements for various DLC foil thicknesses reveal reproducible profiles when varying the peak intensity over 1 order of magnitude. This confirms that plasma formation consistently occurs during the steep rising edge, with the temporal evolution remaining unchanged. The time axes in the transmission profiles are expressed in relative times, with the plasma formation shifted by approximately 1 picosecond when varying the peak intensity. The results indicate the formation of highly overdense plasmas, characterized by electron densities significantly exceeding the critical density. Consequently, significant optical tunneling of the probe through the plasma slab is expected. The interaction between a high-intensity laser pulse and a diamond-like carbon, DLC, foil is the subject of this research paper, focusing on plasma expansion and its effect on probe light transmission. Both experimental measurements and numerical simulations are presented to explain the observed transmission profiles. A unidimensional particle in cell, PIC, code and a solid-state interaction, SSI, model were used for simulation. The PIC code demonstrates a rapid decline in transmission due to The author's approach provides a detailed description of the plasma formed by pre-expanding a thin foil using a controlled prepulse, which is of fundamental interest and crucial for finding the matching laser target conditions required for the Rita regime. The authors employ a combination of experimental and theoretical methods to investigate the interaction between a high-intensity laser pulse and a plasma slab. In the experiment, the transmission of a probe pulse through the plasma is measured, and the conversion of the probe wavelength to time is calibrated using an additional prepulse with an adjustable time delay. The analytical model for optical tunneling is based on Maxwell's boundary conditions at the front and rear sides of the plasma slab. The transmission is calculated using equation 1, which takes into account the dielectric function, plasma density, and probe wavelength. To simulate the interaction, two complementary models are used: the particle in cell (PIC) simulation and the solid-state interaction (SSI) model. The PIC simulation, employing the SMILEI code, models the interaction between the laser pulse and the plasma, including multi-photon ionization, field ionization, and collisional ionization. The simulation box has a length of 1 micrometer and a cell size of 0.156 nanometers, with the target modeled as a slab of cold carbon atoms at solid density. The pump laser has a central wavelength of 1030 nanometers and enters the box from the left, with a temporal resolution of 5 × 10^4 fs. The SSI model, adapted from Ref. 33, describes ionization in solids using a set of rate equations that account for the electron dynamics in the conduction band. The model includes primary photoionization, oniphoton absorption, and impact ionization, as well as collisional ionization and electron avalanche ionization. The free electron density is calculated as the sum of the electron densities in each conduction state. The authors note that the SSI model remains valid as long as the emptying of the valence band is not accounted for, and the free electron density can exceed tens of critical plasma densities. The authors employed two-temperature model, TTM, to describe the interaction between electrons and ions in a solid target. The TTM consists of two coupled equations that account for the energy exchange between electrons and ions. The electron and ion temperatures, T and TL, are described by the heat capacities Ce and Cl, respectively. The electronion energy exchange factor G is evaluated using the Drude model, which takes into account the electronfin collision frequency nu-pH. The authors also introduce a two-step interaction model, TSI, that simulates the interaction between the laser pulse and the solid target. In the TSI model, the PIC simulation starts with a homogeneous plasma slab with a density Ne, m approximately equals 70 Nc of the initial target thickness. The electrons and carbon ions are initialized with Maxwell-Boltzmann distribution functions with temperatures T, m and T, m, respectively. The plasma is modeled as partially ionized with a mixture of single and double ionization states of carbon ions. The research paper discusses the dynamics of femtosecond laser-induced damage in dielectric materials, emphasizing the need for a unified model that can describe the entire process from laser-plasma interaction to material damage. The authors propose a hybrid computational model combining particle-in-cell simulations for plasma dynamics and a hydrodynamic code for solid-state response. This approach allows for an in-depth analysis of the laser-plasma interaction and subsequent damage mechanisms. The model is validated by comparing simulations with experimental data on fused silica, accurately predicting observed damage patterns and identifying primary damage mechanisms. The study also explores the role of defects, pulse duration, and intensity on damage, showing that shorter pulses lead to more localized damage and higher intensities result in more extensive damage. This work presents a novel approach for understanding femtosecond laser-induced damage, providing a comprehensive framework for simulating the entire damage process. In the concluding section of this research paper, the authors summarize their findings and contributions to the field of machine learning. They emphasize that their proposed approach has significantly improved upon existing models in terms of both accuracy and efficiency. This is attributed to the novel combination of techniques from deep learning and traditional statistical methods, which allows for more robust and generalizable models. The authors also highlight the potential applications of their method in various domains such as computer vision, natural language processing, and time series analysis. They suggest that future research could explore further refinements to the algorithm or its adaptation to other types of data. A key aspect of this page is the detailed analysis of the results obtained through rigorous experimentation on multiple datasets. The authors provide a comprehensive comparison with state-of-the-art models, demonstrating the superior performance of their approach across different evaluation metrics. This strengthens the argument for the validity and impact of their contributions. Additionally, the authors address potential limitations and assumptions made in their study. They acknowledge that the current implementation may not be optimal for all types of data and suggest areas where improvements can be made. This openness about the limitations adds credibility to the research and encourages further exploration by other researchers in the field. The paper concludes with a discussion on the implications of these findings for the broader machine learning community. The authors emphasize the importance of interdisciplinary research that combines insights from various fields to drive innovation. They believe that their work serves as a testament to the power of such interdisciplinary approaches and hope it will inspire future investigations into similar directions. Overall, this final section reinforces the significance of the research presented throughout the paper, emphasizing its potential to influence future developments in machine learning and related fields.